boys, how are you doing? Yeah. So, who will remind me um, our derived equation last time for speed of wave along a string, which are two parameters we have to take into account. It's tension and density. Tension and like linear density of the string. So that was our most important contribution last time. Today we will consider several topics. So first of all, we discuss uh, energy transfer of a wave, interference of waves, and we will introduce sound waves. So let us jump into it. So we will consider some simple harmonic oscillator which is attached to the end of the string, so it creates a wave, and our goal will be to consider some small element with mass dm. So let's consider its kinetic energy. Um, so obviously its motion will happen only along axis y because it doesn't move along axis x. So kinetic energy in general can be expressed as 1/2 m times v squared. So in our particular case, we deal with small elements, so we will write dk is equal to 1/2 times dm times v squared. So we derived previously expression for velocity as a function of time for some given wave function. So that was v, like speed, is equal to minus omega times a times cosinus kx minus omega t plus plus phi. Here, for simplicity, we will consider phi equal to 0. So, as a result, when we substitute it in our expression for kinetic energy of this small element, dk will be equal to 1/2 dm times minus omega a times cosinus kx minus omega t, and phi we consider equal 0. And this is in second power. So next step, we can consider that dm is equal to mu linear density of the string times dx, length of this small element. So taking this into account, we can write further, will be 1/2 mu times omega square a square cosinus square kx minus omega t and times dx. So that is kinetic energy of this small element. Now we want to have a information about kinetic energy of some more defined lengths of the string. Let us consider the wavelengths. So please remind me, what is the definition of wavelengths. In the same phase. Yes, so we pick up two maximum. So these are points in the same phase, like closest points in the same phase. Distance between will be down. So now what we want to know like the total length of the string within this wavelength. What kinetic energy it possesses. So for that reason, we need to divide this total length in small elements and then integrate, so sum up total kinetic energy. So total kinetic energy per one wavelength will be equal to integral from 0 to lambda dk. Or we get here our constants out, 1/2 mu omega square a square. And obviously, another thing which I forgot here, we need to specify some moment of time. So that will be, let's t equals 0. So in that case, we will have integral from 0 to lambda of cosinus square kx dx. So we determine total kinetic energy per wavelength of the wave which is traveling along a string at some fixed moment of time, given moment of time, which we choose to be t equals 0 here. So now, if we consider trigonometric identity that cosinus square alpha is equal to 1 plus cosinus 2 alpha divided by 2. So we can transform this integral into two integrals because we have like two terms here. And then eventually we will get the expression for this integral 1/4 times mu times omega square times a square times lambda. So that is the total kinetic energy which we have per one wavelength in this specific case. However, it's not total mechanical energy because besides kinetic energy, we also have some potential energy. We have some elements of the string located in different position to other elements. There is some tension, and that all combined provides certain potential energy in the present in the string along this wavelength. So if we consider that potential energy also in similar way per one wavelength, so potential energy per wavelength, we will get the same equation. It will be 1/4 mu times omega square times a square times lambda. So now we want to know the total mechanical energy, which is the sum of kinetic and potential. So E lambda will be equal to kinetic energy plus potential energy per one valence, and that will be 1/2 mu times omega squared times a squared times lambda. So now, tell me please, since we already know what total mechanical energy we have per unit valence, what will be the rate of energy transfer? Rate of energy transfer means energy per unit time through a cross section of a string. So we can pick up any point on this string, should make a cross section, and through this cross section, per unit time, how much energy will be transferred? Any suggestions? You should look closer to this, where it is. No, it's a bit lower. Should look closer to this equation. And we understand that this equation gives us the total mechanical energy per one wavelength of this wave. So what will be the rate of energy transfer through a given cross section of the string? One more, like closer hint here. Look at this lemma. How much it takes, how much time it takes for a wave to travel distance which is defined by wavelengths. One period. So if we know total energy, which is per wavelength, and we know to get the rate of energy transfer per cross section, what we need to do, we need to divide this total energy by time, how long it takes to travel along the string. This how long for this amount of energy it takes to travel along the string. So that's why power, which is rate of energy transfer, energy per unit time, will be equal to energy per one wavelength divided by T, capital T, which stands for the period of the wave. And that will be 1/2 times mu omega squared times a squared times lambda divided by T. So now look here closer. What is this? This is distance divided by time. That is speed of wave. So we can write here that it will be 1/2 times mu omega squared times a squared times v. So that is the equation which describes energy, like rate of energy transfer through a cross section of the string. Take a look here and tell me what are the dominant factor which define this power. Dominant parameters. Obviously those where we have second power. So angular frequency and amplitude will define mostly the energy which is transferred by wave traveling through a string per unit time. And that is actually valid for all other types of waves. Frequency and amplitude, these are the dominant factors which will define how much energy is transferred by this wave. So now let us consider so-called interference of waves when we have superposition, like overlap of two waves. So let's consider two wave functions, y1 x t, function of position and time, will be equal as amplitude a times sinus kx minus omega t plus phi, and another wave function y2 x as a function of position and time equal to amplitude times sinus kx minus omega t. So what is the difference between them? They are quite similar, but the difference is this phase shift phi. So there is some phase shift between these two waves, which are uh, of the same amplitude and frequency. So these waves interact with each other, so-called superposition of these waves, and we get some resultant wave which is like displacement of medium is the sum of displacement caused by each of these waves. So in this case, um, since it's superposition, we just sum up two wave functions and get the result. So here is yr will be resultant wave function. It's a function of position and time. Will be equal to y1 x t plus y2 x t. That is equal to a times sinus kx minus omega t plus phi plus a times sinus kx minus omega t. So now, if we consider another trigonometric identity, which is the following: sinus alpha plus sinus beta can be represented as 2 times sinus alpha plus beta over 2 times cosinus alpha minus beta over 2. So applying this to our previous equation, we will get the expression for the resultant wave function as following. So it will be 2 times a times sinus kx minus omega t plus phi over 2 times cosinus phi over 2. So for final form, we need to rearrange it a bit. So we have in front of sinus all time-independent parameters here. Y as a function of r, x t is equal to 2a times cosinus phi over 2 times sinus kx minus omega t plus phi over 2. So that is the resultant wave function of interference of two waves with some phase shift phi between them. So here we have the amplitude value, which is a function of phase shift phi, and this is like pretty much similar what we had before. We have the same frequency doesn't change. However, amplitude is changing, and it becomes a function of initial phase shift between two waves. And let us consider two extreme cases. So when we have cosinus phi over 2 equal to unity, that's the maximum value, and cosinus phi over 2 equal to 0. So for this first case, what condition should be true for phi? It should be equal to 0. So that will be when we get the value for cosinus equal to unity. So in this case, what we have? We have y r as a function of x and t equal to 2a times sinus kx minus omega t, because phi is equal to 0. So actually it is the same as expression for second wave we had previously. However, here we have 2A. So that stands for so-called constructive interference when we have overlap of two waves in the same phase. So they um, kind of just enhance each other because they come in the same phase. So instead of just single A, we get amplitude twice larger. Or if their amplitudes were not the same, so we will get just sum of two amplitudes of our waves. But we consider the same amplitude, so it will be twice larger. So what condition will satisfy this case? Phi equals to pi. And that is when we have opposite phase of two identical sinusoidal waves. So they come in opposite phase means that maximum of one wave correspond to minimum of another wave. So when they overlap and their amplitudes are the same, so that will result in y r x t equals to 0, means there will be no any wave anymore because these two waves came into contact, into interaction and superposition in opposite phases with identical amplitudes. They cancel each other, and that will be so-called destructive interference. We do not get any resultant wave. So with this, we proceed further to some topic which probably one of the most common for our everyday life in terms of waves application, that is sound wave. And obviously we deal with it every day. Right now you listen, and who listens, maybe someone not, but that's okay. So those who listen, they hear my voice, which is a sound vibration spreading in um, air, which in this case is medium, where these waves are traveling. Um, if there is no air, well, I could try to say something for short time, but you would not care because there is a requirement. You should have a medium in order to spread sound waves. And tell me, what do you think? Which type of waves is sound wave? We consider two. No, that longitudinal wave, because in this case we have elements, like if we consider some small element of air, it vibrates, like this vibration happens in like parallel to the direction of sound wave propagation. So it's different from wave which is traveling along a string. So therefore, instead of wave function as y function of x and t, here we will consider for sound waves another wave function like s as a function of x and t, and that will be the only difference. We just need to understand that in previous case displacement of small elements was happening in y direction. In this case displacement happens in x direction. Other from that, they are the same. So let us consider some model system which creates sound. We have some cylinder filled with air, and let's consider these are particles of air. And we have a piston which is vibrating, moving back and forth with certain frequency. So that creates some, first of all, motion, like displacement of these small elements of air. Let's show it like this. So it moves along axis back and forth along axis x. And now let us delete this. So it's described by this wave function. So we can write here as maximum, which is maximum displacement, times whatever we consider, which function. Let's see. Yeah, cosinus. Okay, cosinus kx minus omega t. So that is the wave function which describes displacement of small elements of air when sound wave is traveling along this cylinder. As a result of this vibration of the piston and motion of small elements of air, we create some areas with higher and lower pressure in this cylinder. So if we look here, uh, let's say this will be pressure or change in pressure, delta P, as a function of position x. So we will see something like this. So it will go up, down, and again up and down. So that is the function which describes change in pressure inside this tube. So now what we want to do, we want to find the relationship between the change in pressure and displacement of small elements of air S. Why? Because when we are dealing with sound waves, we do not measure displacement of air. We just don't see the small particles. That could be one reason. Um, and it's much easier for us to carry out reliable measurements of pressure change rather than identify some elements of air and measure how they are displaced. So it makes much more like practical sense to deal with pressure change. However, so we have this wave function for displacement of elements, which we can kind of borrow from previous discussions. But we don't have the relationship with pressure change. So in order to make this step from displacement of some elements of the medium towards the pressure, we need to introduce such parameter as bulk modulus. So pressure change, delta P, is given as minus capital B, which is bulk modulus. It's a feature of the medium, like some elastic feature of the medium, times delta V over VI. So we have delta V is change of volume, and VI is the initial volume. So this introduces the relative change in volume of the medium times this bulk modulus, and that results in change of pressure in the vicinity of this area of the medium where all these changes are happening. It is possible to show that that should be equal to minus b times partial derivative of displacement, like wave function, over position when we consider time as a fixed parameter at some given moment of time. So now we have the relationship and we have the wave function for displacement. So let us get the wave function for change in pressure. So we can write here that delta P will be equal to minus B plus multiply d over dx, and here we substitute expression for the wave function of the displacement of air elements. So we have S maximum times cosinus kx minus omega t. So let us take this derivative, like partial derivative, assuming that t is a constant. So we get, actually minus will go away. Yes, so we can skip it. It will be b times S maximum times k. And here will be sinus kx minus omega t. So that is our result. So these three coefficients in front of periodic function will give us, what's happening? Interesting. Okay. This will give us delta p maximum times sinus kx minus omega t. So now look at the wave function for change in pressure and wave function for displacement and tell me what is the difference between them. Exactly. What does it mean? In opposite phases. Yes, they are in opposite phases means that maximum displacement corresponds to minimum change in pressure and maximum change in pressure corresponds to minimum displacement. So that you just keep in mind that there is such a relationship. Other from that, they follow pretty much the same um, dependence, but just in opposite phases. And of course, there is this relationship delta P maximum, how you go from displacement to change in pressure, that is B times S maximum times K, which K, what is this? Is wave number. And that is defined as 2 pi divided by lambda. Just as recall. So we have this relationship and we have also the wave function which describes change in pressure. However, so it looks like from first point of view that we accomplished our task. However, this parameter b is not very practical parameter for applications because we don't usually deal with it. It would be much better if we have an option to deal with density of the medium instead of this bulk, bulk modulus, because density of the medium is like something what is everywhere available and easy to measure. So in order to have a transition from this bulk modulus to density, we need to introduce first the speed of sound. And speed of sound is given with this simple equation, which is bulk modulus divided by density of the medium, rho. By the way, you can compare this to the speed of wave traveling along the string, which we derived last time. It was tension divided by linear density. Oops. You see the similarities. Moreover, I would tell you that for any waves, any types of waves, there will be something like this in terms of speed of this wave. So we will have in numerator some elastic parameter of the medium, and in the denominator we'll have some, let's call it, inertial parameter of the medium. And in this case, we deal with bulk density, here with linear density. So if we want to get a medium with very high speed of sound, we want very strong material which resists for compression very much and lightweight. So if we consider under normal conditions speed of sound for air, V air, that will be something around 340 meters per second. So that is something about 1/3 of kilometer per second. So if you see lightning, assuming that speed of light is very large, so the signal comes to our photodetector, which we call eye, instantaneously, then you count the seconds until you hear the sound of the like thunder. You divide it by 3 and you get the distance in kilometers approximately. So if you repeat it 2 times and you see that this distance getting shorter, good point to find somewhere too high. So that is about speed of air sound in air. However, if we consider speed of sound in titanium, it's such a very strong and light metal, which is widely used in our airspace industry, because you want to have strong and light constructions there. So that will be around, like, even actually exceed 10,000 meters per second, which is insane. It's almost second uh, space speed, which is escape speed from planet Earth. We were calculating it was something 11.2 kilometers per second, and for titanium we get 10 kilometers per second. So now, when we have this equation, which gives us the speed of sound, and keep in mind that speed of sound we can measure very easily. Also, we can measure easily this density, rho. So we can express this bulk modulus, which is not so straightforward to measure, in terms of these two parameters. So bulk modulus will be equal to density times v squared, speed of sound in second power. Also, what we need to do, again, I recall that this wave number is 2 pi over lambda, and that is equal, well, what we can do here, let us multiply and divide by frequency. So tell me, what do we have in numerator? Angular velocity, omega, and what we have in the denominator? Speed of sound. So that will be v. Now we recall this previously derived relationship between change of pressure and displacement, that was b times s maximum times k. And now we substitute, instead of b and k, our expressions. So what do we get? We get rho times v squared times s maximum times omega divided by v. We cancel out this, guys, and eventually we get rho times v times omega times s maximum. So now what we have, we actually accomplished one more time our task relating change in pressure in medium where sound wave is moving with displacement of this medium because of sound wave, but now we operate with parameters which are easily measurable. So density, speed of sound, and frequency of the sound wave. So that is useful for further considerations. And obviously, in real life, we operate with measuring change of pressure. However, it gives us a relationship between two wave functions which describe both displacement of the medium and uh, change in the pressure. So let us now summarize our discussion for today. We first of all consider how energy is transferred through a string when there is some running wave through the string. And we have shown that the rate of energy transfer means energy per unit time, which travels through a cross section, like any cross section of the string, will be mostly defined by two parameters, two dominant parameters, because they have the second power next to them. So that is angular frequency and amplitude. That is valid for any type of waves, including even electromagnetic waves, which have completely different nature, physical nature, but also the amount of energy which they transfer through the cross section of some area, like some space, per unit time, they also will be proportional to frequency and amplitude in second power. Um, then we consider the interference of two waves which possess the same frequency and the same amplitudes. We figure out that after superposition, we get a resultant wave, which, like where the amplitude will be phase dependent. Two extreme cases, when phase is equal to zero, we get interference of two waves which are in phase. Then we just twice increase the amplitude. If these waves are coming to interact with each other in opposite phases, they just cancel each other and we don't have the oscillation as a result of this interference. We introduced sound waves, which are longitudinal waves which can spread in different medium. Most common for us is air, but can travel in, actually can much faster travel in denser mediums like metals. In particular, titanium is probably one of the, we would consider pure metal, not alloy. Some special with some specifically modified properties. That's probably the most favorable environment for sound wave traveling. And the key thing here was to find the relationship between the wave function which described displacement in medium and change of pressure. We are introducing bulk modulus and speed of sound. We could come to this equation which gives this relationship in, involving quite easily measurable parameters, which is density, speed of sound, and angular frequency of the sound wave. So with this, thank you very much for attention. We will continue tomorrow because we study for Monday. And we will continue further consider sound waves. Have a good evening. See you tomorrow.